everyone, Commander Josh Hawkins here, and this will be my fourth transmission back to Earth. If you haven't already received my last broadcast, please check your computer's archives for a link below. I'm sending this broadcast out in hopes that it reaches you with more details about my voyage and our mysterious Milky Way Galaxy. My mission is to explore and record all the wonders our galaxy has to offer, and so far I've come across many incredible sights. I've seen everything from worlds with Earth-like environments harboring primitive water-based life, to a planet bleeding molten iron across its surface. I've seen moons with mountains reaching tens of kilometers high that would dwarf even the tallest mountains on Earth, and the wreckage left by an unfortunate explorer who must have gotten a little too close. As an explorer, no matter what your intent when you leave the bubble, whether it be to survey, to catalog, or simply to appreciate the wonders out there, we all share one thing in common. Each time we make a jump, we land on a new star, or in some cases the remains of a star. But what do we really know about the stars? What are they made of? How did they form? And since everything in the universe is connected, how are we connected to the stars? In this transmission, I hope to explore and answer some of these questions. Welcome to Exploring the Milky Way Galaxy, Part 4. Since my last transmission, I've traveled another 3,000 light-years towards the heart of our galaxy. I passed through and mapped a small emission nebula, and marveled at how the sky has changed along the way. What was once just a black backdrop with a sprinkle of stars, now appears as a backlit canopy with thousands of holes punched in it. 4 centuries before the invention of hyperspace, the closest we were able to get to the stars was by gazing through a telescope. We classified the stars based on their spectral characteristics. Most stars were classified under the Morgan-Keenan system using the letters O, B, A, F, G, K, and M, a sequence that represents the hottest, type O, to the coolest, type M. Although there are many other star-like objects that didn't fit into this classical system, these were the ones that we saw most of when we looked up into the night sky. The first telescopes were simple devices that used a concave glass lens as their objective to form an image. These refracting telescopes were very popular in the second half of the 19th century and were used by famous astronomers such as Galileo and Johannes Kepler. Kepler improved on the design by using a convex lens as the eyepiece, which improved its magnification. But the refracting telescope was limited in many ways, and was eventually superseded by the reflecting telescope, which used a curved mirror instead of a lens. As light passes through a lens, it stretches, creating an effect known as chromatic aberration. But light reflected off a mirror did not, which gave them a distinct advantage. Using mirrors also allowed for much larger apertures, making the tube of the telescope a lot shorter, which in turn reduced their cost and allowed for the construction of much more powerful telescopes. But whether we used a lens or a mirror, when trying to see the stars from the ground, we've always faced a similar problem: our atmosphere. Earth's atmosphere scatters the light that passes through it. It becomes blurred and speckled. This is what causes the stars to twinkle when you gaze up into the night sky. If we removed our atmosphere, the stars would resolve into a fine point of light, and the twinkling would stop. Of course, without our atmosphere, we would have a lot of other problems, so clearly we had to make do with what we had. On April 24th, 1990, we overcame this obstacle with the launch of the Hubble Space Telescope. When Hubble sent back its first images, we finally saw the stars with no interference from our atmosphere, and what a sight it was. The universe was literally filled with stars, billions upon billions of them, and the discoveries Hubble made changed our view of the universe. After Hubble, we made many more advances in the fields of astronomy. Our Earth-bound telescopes grew larger and larger, and eventually, using adaptive optics and another new technology called optical interferometry, we were finally no longer limited by our position on the ground. Interferometry allowed us to combine the light from several large telescopes to create a virtual telescope, which not only improved the clarity of the image, but allowed us to see the stars with 50 times the resolution of Hubble, expanding our view of the cosmos even further. But as we continued to push these boundaries, we once again found ourselves limited by our technology. It took another 100 years before we discovered hyperspace, and astronomy took another major leap forward as we were finally able to visit the stars that before we could only look at through a telescope. Although we had learned much about them already, nothing compared to a close-up examination and comparison of the different stars in the galaxy. From cold dark beginnings to their magnificent and sometimes explosive end, the life of a star is a delicate balance between gravity and radiation pressure. It begins inside a massive cloud of dust and gas composed mainly of hydrogen when a dense sphere of gas begins to form. As the sphere grows in size and mass, its gravity begins to squeeze the molecules of gas closer and closer together, heating them up in the process. When the particles inside this ball of gas get close enough, they begin to fuse together, forming helium, and a star is born. Inside the core of a star, the thermal energy being released from the fusion process pushes against the gravity, which is constantly trying to pull it inwards, and the star achieves equilibrium. We call this process the main sequence. Lower mass stars consume their fuel slowly and can remain in the main sequence for billions of years. Our Sun has been a main sequence star for 4.6 billion years, and will remain one for another 5 billion years still. But the process of fusing hydrogen into helium doesn't last forever. For stars up to 1.5 times the mass of our Sun, running out of hydrogen forces it to start fusing helium into carbon and oxygen. When this happens, the core grows denser and begins to contract, causing its outer layers to expand and cool. As the star itself grows larger, its brightness grows ever dimmer. It has now reached the last stages of its stellar evolution, and it's called a red giant. Eventually, this enormous star will shed off its outer layers to form a planetary nebula, leaving a spent core composed mostly of electron-degenerate matter at its center. These stellar remnants are very dense, about the same mass as our Sun, but fit into a space only as big as the Earth. This is a white dwarf, and although it no longer has the ability to fuse carbon into heavier elements, it will remain hot for another 14 billion years as it slowly cools and eventually fades away. However, this is not the fate of all stars. Stars more than 1.5 times the mass of our Sun don't die with a whimper. Similar to their smaller cousins, massive stars also begin to grow as they start fusing heavier elements, but their enormous mass causes them to burn much hotter and consume their stellar fuel at a much faster rate. As these massive stars run out of hydrogen and helium, they continue the fusion process with carbon fusing into neon, then oxygen, silicon, and finally iron. Iron doesn't produce energy when it fuses, so it begins to build up at the core, and once enough iron builds up, the star no longer has enough energy to hold back the force of its own gravity, and the results are spectacular and catastrophic. The outer layers of the star collapse inward at almost the speed of light and smash into the core, bouncing off at incredible speeds, causing one of the largest explosions in the universe, a supernova. The incredible pressure from the shockwave is enough to fuse iron into all the heavier elements in the universe, and the force of the explosion sends them off into space to seed the next generation of stars, planets, and even life itself. There is still much we need to learn about them, but one thing we know for certain is that without them, none of us would be here. And not just because they warm our planet and give it the ability to sustain life, but because the very elements that formed our planet and make up life as we know it are created within these stellar crucibles. The carbon in your muscles, the calcium in your bones, and the iron in your blood are elements that came to be when a massive star exploded and sent its remains off into space. You and I and the world we know exist because of them, and that is how we're all connected. Not through our media, not through our social networks, but through the very stars themselves. So the next time you look up into the night sky and feel very small compared to the vastness of the universe, remember that you are connected to everything around you because we are all made from stars. Please click the like button below and don't forget to subscribe. Commander Josh Hawkins, signing off.